Hi everyone, welcome back to my math teaching channel online today. Today in this video, I am talking about the application of derivative in calculus, and I will solve the swimming pool problem. So let's take a look at the question, and I'm going to read it out loud to you. Now, this is a question I found very interesting. It covers a lot of geometry shape and how to draw the three-dimensional figure, how to break it down into mini section and combine and get the answer. So let bear with me. I hope that this question is interesting enough to make you watch the entire video from the beginning until the end, so to see how the concept, a complicated concept, look like in terms of geometry. So let's get in right into the question now. I'm going to read it out loud to you. A swimming pool is 12 meters long and 6 meters wide. 1 meter deep at the shallow end and 3 meter deep at the deep end. Water is pumped into the pool at the rate of 1/4 at the rate of a quarter meter cube per minute. And there is 1 meter deep of water at the deep end. What percent of the pool is filled? That's the question one. Question two, at what rate the water level is rising? Okay, so let me summarize the question and the geometry shape for you to see. So we have a big swimming pool with the shape. What kind of shape is that? It's a trapezoidal prism shape, right? We call it prism because three-dimensional picture. So I try to sketch the three-dimensional picture here very look as clearly as I can, right? This is a complicated diagram, and let's find out. So I'm going to summarize the question, right? So we have a big swimming pool, and the length of the pool from here to here, the same length from here to here is 12 meters. The width of the pool from here to here is 6 meters. And to design it in a safety way, they make a shallow section, shallow end, the two end. One is deep and one is shallow for the, like the young kids jump in the pool. So from the shallow end, with the height from here to here is 1 meter, the same like from here to here. And the deep end from here to here, 3 meters. But they also say that there is a 1 meter deep. So from here to here is 1 meter deep of the water level. So the triangular, the blue triangle here, it represents the water, right? At the deep end already in the pool. So they pump in the new water, and to solve this problem, I'm going to cut this figure into 3 figures here, right? One figure, big one. So this one here, I call it a triangular prism because the base of it is a triangle, right? If you turn it upside down this way, right? This become the base, and the base here have a shape of triangle. And if you turn it upside down, this become a height of the prism, right? But the base of it is triangle. So I call this a triangular prism. And if you look at from here to here, all the way here, right? This is the shape of rectangular prism. And if you look at, and I demonstrated here, so I cut this big one, I put it down here. And if you look at from here to here, to here, to here, to here, this second section here is the third figure. I cut it and I put it down here, right? So I sketched 3 figures down here for you to see the components of the swimming pool look like, the structure of it, how it looked like. Anyway, I'm going to talk about to find the volume of any three-dimensional object. Let's say you have a cylinder here. To find the volume of cylinder, you always use the area of the base and the bottom, or the top, one of them, right? The same. Use the area of the base times with its height. So for any object, you use the base area times with its height. That become a volume. Now this volume, if I stand it down like that, or I stand it up like this, the same. It's no different, right? So you can see that whether the figure here, I turn it lie down, I turn it like this figure, if I turn it upside down this way, the volume is the same. It's just the shape of triangular prism, right? Just like this cylinder here, I lie it down and I stand it up. So if you turn this base down and you stand this up, this become a height of the prism. As well, this trapezoidal prism here. If I turn this down this way, I turn it upside down, right? I turn this way, this become the height of the prism, right? This become, and this is the base. And the base here have a trapezoid shape. And that's why it's a trapezoidal prism. The base here have a triangular shape. And that's why we call it triangular prism. The base here have a rectangular shape, and that's why we call it a rectangular prism. For any volume of any object, it always equal the base times with its height. Equal the base here times with its height here. And depend on the base shape. If the base shape is a circle, you use the formula of the circle to time with its height. If the base shape is a triangle, you use the area of the triangle times with its height. If the base shape is a rectangular prism, you use the base shape of a rectangle, area of the rectangle down here, times with its height. So that's the concept of finding the volume. So now let's get into the first question. How I'm going to find the first question. So let's say to answer the percentage, what percentage the pool is filled, I have to find the ratio of the volume of the water, which is VW, I call it V water, right? Divide the volume of the whole swimming pool, and I call this VF, the same like V full, right? This is like V water. Divide by V full times with 100. And that's how I answer question A. Because the question asks for what proportionate in percentage of the volume, the capacity, the volume of the water compare with the whole volume of the swimming pool. So that's on the question asked. So to find, we have to find volume of water, and we have to divide it by, to find the ratio, divide by the big volume of the big pool of the whole, I call it V full, times with 100 to get the percentage, right? Now, how do we find the volume of the big pool? The volume of the big pool is easy because we have all the information, right? So I'm going to write down all the information for that. And I want to say V full, VF will be equal the area of the base, right? The area of the base. And the area of the base here is the area of the trapezoid is the short length adding with the long length, divide by 2, take the average of these two, time with the height of the trapezoid. And the height of trapezoid here, we know from here to here is 12. So it will be equal 1 meter, adding, which is the short one here, adding with the long one here, which is 3 meter, divide by half to get the average, time with the height of the trapezoid, which is 12 meter, times with the height of the prism, which is from here to here, which is 6. So 1 at 3 divided by 2 times with the height of trapezoid, which is 12, times with the height of prism here, which is 6. So this will be equal 144 meter cube. Volume, full volume of the trapezoid. Now we've progressed to find the volume of water. And I call the volume of water VW, right? Shortcut. So volume of water is a little bit complicated because at this moment, we know from here to here is 1 meter, from here to here, right? So we can find the area of this triangle, right? By height, this is the height of triangle, times with its base divided by half. That is the formula to find the area of triangle. Height times base divided by 2. Times width, so height times base divided by 2. Times with the height of the prism here, it will give us the full volume of triangle. Unfortunately, we don't know how far from here to here. The length here of the water, the length of water from here to here, we don't know, right? We just know the full length from here to here is 12 meters based on the construction of the pool. They say from here to here is 12. But we know from here to here is 1 meter deep. We don't know from here to here, right? So I put the question mark here. We have to figure out the L before we can find the volume of the water, right? And how do we figure it out? So our first job will be find L first, okay? And to find L, you will use the ratio problem so that you can solve for L. And how do we put in the ratio problem? Now, if you look at the big trapezoid here, right? You look at the big shape here, and I think that I lose a part of my writing over there. So I'm going to adjust the computer. Sorry about that, so that you can see what I put before. So before I put to find the ratio, you have to find volume of water divided by volume of the full pool times with 100. So V full will be equal 1 at 3, which is the area of trapezoid, times with the height of trapezoid, which is 12, divided by 2, times with the 6 from here to here to get 144 meter cube. Now we find the volume of water, but however, volume of water here, we don't know the length from here to here, right? So to find the length from here to here, we have to use a ratio. And how do we use the ratio? We will look at the big trapezoid here, right? Big shape here. So we will say that this small one, right? This one over this one, right? 1 over 3 will be equal x over 12, right? To find x. So we can find the little portion here first by comparing the ratio of the small trapezoid here with the whole big trapezoid, right? That's how we take the ratio form. We find this length of the small trapezoid, compare with the big length of the big trapezoid. So we say 1 over 3, 1 over 3 will be equal, so this length over this length will be equal x over, from here all the way from here to here, right? Over 12. So do cross multiply, we solve for x. So we have 3x equal 12. So therefore, x equal 4. So now we know x equal 4. If we know from here to here equal 4, from here to here, then we can figure out from here to here for the water, because this length from here to here the same like this length, right? So we use the 12, subtract the 4. So therefore, now we know L. L will be equal to 12 meter, subtract 4 meter, equal 8 meter. So now we know L here is 8 meter. The length of the water here, this one, equal 8 meter, right? So now we can find the volume of water easily. So volume of water will be equal 8 meter base times height, which is 1 meter, divided by 2, right? That's the area of triangle, times with 6 meter, the height of the prism, right? So that will give us 8 divided by 2 is 4, 4 times 6, 24. 24 meter cube. So now to answer A, we will say VW divided by V full, VF, equal 24 divided by 144 times with 100. That will give us 16.66, round off becomes 17%. So now we know the answer for A is 17%. So now we will answer what percent of the pool is filled. So we will say 17% of the pool is filled, right, with the water. So that's how we do A. Now, because this is a complicated and long problem, I will have to erase this bar, right? So that I continue to do the second question. At what rate the water level is rising? So after we done this, I'm going to have to erase it because I don't have enough room. And I want to keep this bar for this figure so that you can see it, right? So I'm going to have to erase this part, but I hope that you understand up to here, right? So now I'm going to erase this. Okay, so now let's go to at what rate the water level is rising. So to find the rate of the water level rising, I'm going to say let H be the level of water. Let H be the level of water rising. So remember, we don't care about the level at the beginning anymore. Now we're talking about water come in, right, with the new water. So we have to totally cut off this triangular prism. We don't care about that anymore. So we left with the remaining of the pool is this big figure here, the rectangular prism, which I call figure 2, and the trapezoidal prism here on the right hand side, which I put it down here. This is the trapezoidal prism, and I call it figure 3. So now we ignore figure 1 because we're done with it. So now we look at this big chunk here, right? Empty chunk here. Not talking about the blue color down here anymore. We cut it. So now look at these two figures, 2 and 3. Let's talk about the water level rising. Now, to solve the derivative problem, what you should know is what is a fixed number we can use and what is a variable. What is the unknown thing we don't know, right? And unknown thing we don't know, we call a variable, we call a letter. So we say let S be a shadow or let L be the length, or let H be the height of the water level rising. And that is the unknown variable. And we put in the equation a function, find the volume in terms of the H, or in terms of X or whatever, Y in terms of X, or V in terms of H, right? So we have to know the variable. What is our variable in here? The height, the level of water is a variable. We don't know how high it rises, right? And it keeps changing. At the start, it rises a little bit, and then it rises more and rises more. And that's why we call a height is keep changing. We call the rate of change, right? But the fixed number is the 6 meter wide and 12 meter long. That is a fixed number. So let's figure out. So let H be the unknown variable, right? Be the level of water rising. Now, to make the matter is not so complicated because we pour the water in here. Actually, the water level of rising, right, for these two figures, we can just count them as one level at the same height, right? Let's say you put the water in here, right? And then it's rising here and it's rising here. Even though you can separate them, like this is height 1 and the height of the water level we call height 2, but actually height 1 and height 2 is rising at the same level, right? At the same level for the moment when it entered the pool. It's only slightly a little bit different when it come to this end, right? So a little bit different. We just try to not make the matter so complicated. So let's just say height 1, let's just say height 1 and height 2 here for two figures is the same height, right? Which is the unknown variable of water level rising, right? So I'm going to say, but we still have to calculate the volume remaining of the big figure here. And the big figure here include two figures, which is figure 2, rectangular prism, adding with figure 3, trapezoidal prism. On the right hand side, on the left is a rectangular prism. On the right, this one, right, is a trapezoidal prism. So I'm going to say, what I'm going to say, let V be the volume of the remaining pool, because we cut off the water level, right? We're just talking about the new water come in, okay? So VR will be equal to two figure, which is V rectangle and V rectangle. I'm going to draw a little bit rectangle here, right? Adding with V trapezoidal down here. Or I can call this is figure 2 and this is the figure 3 trapezoid, okay? So V2 and V3, right? The trapezoid. Okay, so V rectangle and the V trapezoid. So that's the remaining of the pool, right? So let's calculate them separately. So VR, V remaining, right? Volume remaining will be equal to the area of rectangle, which is, we know this one is 6, that's a fixed value. We know this is 8, right? From here to here is 8, it's a fixed value. It's just the water level rising, we don't know, and we call this the height, right? So we say the bay is 6 times 8 times with height. So that's the V2. Adding with V3, V of figure 3 will be 1, this is fixed, right? Adding with H, which is the water level rising, we don't know, right? So it will be 1, adding with H, divided by 2. So 1 at H to take the average divided by 2 times with the height. And the height of this trapezoid is 4. So time with 4. And then time with the height of the prism from here to here, which is the same like 6 again, right? So now we have unknown H, but this figure, these number are fixed number, right? So let's calculate. VR will be equal to 6 times A is 48H. Adding with V2 is 4 times 6 is 24. 24 divided by 2 is 12, right? So this becomes 1 plus H times 12. So now VR will be equal to 48H, adding with 12 times 1 is 12, adding with 12 times H is 12H. Now, because we consider height 1 and height 2 for these two figures are the same as the water level rising, so we can add them as a like term. So that 48 at 12 is how much? A at 2 is 10, 60, 60H and 12. So that's the volume remaining. At this point, we can find the dV. We can take derivative of both sides. So we say dV over dt will be equal dV over dH time with dH over dt, the chain rule, right? And what is dV over dt? It's given us 1 over 4. It's right here. It say water pump in the pool with the rate of 1 over 4 meter cube per minute. So dV over dt equal 1 over 4 equal dV over dH. It means we take derivative of this one beyond this, right? So it equals 60. Derivative of 60H is 60 times with dH over dt. So now to find dH over dt, we just pick this number over, right? So 1 over 4 times with 1 over 4 times with 60 equal dH over dt. And this will give us 1 over 240. 4 times 6, 24, yeah. Meter per minute. That's the unit of our water level rising. Okay. Now, this problem, if you separate the water level rising of the height 2 for this figure and consider height 1 for this figure, you can do that as well. However, it's complicated. You have to find the ratio of them, and they're just slightly different. So I ignore that, and I just say the water level rising, when it comes to the pool for both figures, it's just one height, right? And you can see they're very similar height here. It rises here and then rises here for this figure, and it's right here and here for this figure. Now it's slightly a little bit different. It's not much. If I calculate them separate and I add them together and I figure out, so for accuracy, it might be over 100 to 60 or something like that. It's not much, so we can consider choice, so it's not so complicated because this is a very long problem already. So I hope you enjoy this problem, and let me make sure you see everything. Okay, so let me summarize the question be a little bit for you because I might miss some of the part, right? So I say that let H be the level of water rising. So I count the water level of rising of these two figures is just one variable, H, right? Because water coming in and it rises from here and rising, right? It's changing a little bit at the end of this, but we don't want to make it so complicated. So let's put H is the level of water rising for both figures for now, right? So let VR be the volume of the remaining pool. So I calculate VR based on V2, which is this V, volume of this figure 2, adding volume of figure 3. So now VR will be equal area of rectangle, which is 6 times 8, 6 times 8, the base area, time with its height, we call a variable because we don't know how long the water will rise up, and right? So this is a variable, so we put it as the height. Adding with V3, V of figure 3, V of figure 3 is 1 at H. This length, at this length, which is the water level rising again, is a variable we don't know, right? So 1 at H, divide by half, time with the height of the trapezoid here, which is 4, right? From here to here is 4. Time with the height of the volume of the water, which is 6 here, right? Which is the height of the prism, which is 6. So we calculate, we get 48 H, adding with 12, 1 at H, because 4 times 6, 24 divided by 2 is 12. So we distribute this to here, we got 12, we distribute this to here, we got 12H. So because they are like term, we can add 48 at 12H here, equals 60H, right? So volume remaining equals 60H at 12. When we do derivative, this figure becomes 0 because derivative of constant is 0, right? So we have dv over dt equal dv over dh times dh over dt. Now, dv over dh, it means we take derivative of this part. Derivative part is 60, right? This is 0, so we put in 60, that's dv over dh, time with dh over dt. This is the one we want to figure out. So we solve this equation by kick this down here, right? That's the shortcut, you solve it, you know it, right? So it 1 over 240 meter per minute. That's the answer for B. So I summarize that for you, and you can see this is a very interesting problem. We have 3 sections, 3 components, and actually when you draw this shape, right, it takes me a while to try to figure out how to draw it in the 3-dimensional shape, and you know, like on the separate component, trapezoidal and rectangle. So this is I found it very interesting. I don't know if you like it or not. It's a long way anyway. So I just want to share with you, and thank you for watching, and give me a thumb if you like my teaching and like my drawing, sketching 3-dimensional shape, geometry shape on the board, right? This is a lot of work actually, right? But once you get the concept, it's not too bad. And yeah, so I still like this problem. But anyway, I like it. I don't know if you like it or not. But anyway, let us assume you like it and give me the big thumb. And hit like for my teaching video. Thank you for watching. Bye for now. See you in the next video.